For the first 50 years of human spaceflight, the operational standard was defined by waste. Engineers built towering, multi-million-dollar machines to carry payloads into orbit, knowing they would only fly once. It was the financial equivalent of building a commercial airliner, flying it from New York to London, and then scrapping the entire plane upon arrival. Early rocket components were rarely recovered in any usable state. They were left to crash into the sea or drift into the ocean, where corrosive saltwater and the impact of the splashdown permanently ruined their complex systems. To stop this waste, SpaceX had to solve a brutal engineering puzzle. They had to take a 15-story, nearly hollow aluminum cylinder, traveling at 5,000 miles per hour, and fly it backward through the atmosphere to a precise target. This kinetic energy problem was the primary gatekeeper. Until someone could figure out how to stop that falling mass, the high cost of single-use hardware would remain a ceiling for the space industry. The descent begins at the edge of the atmosphere, at the moment of stage separation, when the first stage detaches from the second stage and its orbital payload. To begin the return trip, the booster must turn around. Because wings are useless in a vacuum, cold gas thrusters near the tip of the rocket fire small bursts of nitrogen to physically flip the massive cylinder. Now facing backward, the rocket initiates the boost-back burn. The main engines reignite to act as brakes, canceling out the vehicle's immense forward horizontal momentum. This maneuver redirects the rocket from an orbital arc into a precise return path, targeting a landing zone hundreds of miles away. The margin of error here is tiny. A fraction of a degree off course at this altitude translates to missing the landing pad by miles once the rocket hits the surface. Without mastering this burn in the vacuum of space, the booster would be at the mercy of ballistics, making pinpoint recovery impossible. As the booster drops back into the upper atmosphere, it slams into a wall of air, generating extreme friction and intense heat around the engines. To survive the heat, the rocket performs an entry burn. The expanding exhaust gas creates a physical shield that pushes the superheated atmospheric plasma away, preventing the engine bells from melting as they slow down. Once it reaches the thicker air, the engines shut down, and the rocket deploys its grid fins, 4 metallic control surfaces near the top of the cylinder. These fins pivot independently to manipulate atmospheric drag. It works like a skydiver, adjusting their limbs to steer their fall, guiding the rocket with precision. This unpowered aerodynamic steering bridges the gap. It translates raw falling momentum into a perfectly aligned vertical approach for the final landing. We are now in the final 10 seconds. A 30-ton booster is plummeting straight down toward a rigid concrete pad or a drone ship at sea. This chart shows the primary constraint of the Falcon 9. Even at its lowest power setting, a single engine produces more upward thrust than the weight of the nearly empty rocket. Because thrust outweighs weight, it cannot hover. The computer must time ignition perfectly so velocity hits zero, the exact millisecond altitude hits zero. This results in a violent final deceleration, with the landing leg snapping open just seconds before making contact with the deck. Engineers call this the hover slam. It is a triumph of autonomous algorithmic precision over raw, destructive physical forces. Once the booster is secure, teams inspect the hardware and begin the process of prepping it to fly again. That recovered first stage houses the primary engines and fuel systems, representing the vast majority of the vehicle's total manufacturing cost. This line graph shows the impact of that recovery. Since reusable boosters became the standard, the cost to launch a kilogram of payload into orbit has dropped further and faster than at any other time in history. These new economics make massive projects feasible for the first time, from global satellite networks to deep space missions that were once considered too expensive to attempt. Mastering the physics of landing a rocket was the pivot point. It transformed spaceflight from an expensive act of exploration into the foundation of a permanent orbital industrial network.